This is the third in a series of lectures on differential geometry. In the last lecture, we wrote down explicit examples of manifolds. We wrote down sets, we constructed charts on them, we checked the transition maps are smooth, we checked that the resulting topology is Hausdorff and has a countable basis of open sets. Now that's not typically how in differential geometry manifolds arise. Typically, we already know that they're Hausdorff and that they have a countable basis of open sets because most often the manifolds we'll come across will actually arise by taking smooth maps between manifolds we've already constructed. So now that we have a decent collection of manifolds to start with, we can begin to construct smooth maps between them and use that to construct new manifolds out of old ones. But before we can construct smooth maps between manifolds, we have to just start off with constructing smooth maps between a manifold and the real number line. We have to show that there are actually functions on our manifolds, and that's not obvious. So how can we construct functions? How can we prove that there are some functions? First of all, what do we mean by constructing functions? What are these functions? So a smooth function f taking a manifold to the real numbers, a smooth function means what? It means a function so that its composition with the inverse of a chart is smooth in the sense of being C infinity smooth. That means C infinity for each chart. So our charts are, say, U phi on M, on a manifold M. So that's what it means to have a smooth function. It means that it looks smooth when you look at it in the charts, because the chart identifies with Euclidean space. So the inverse of the chart identifies Euclidean space with a piece of the manifold. So we go from Euclidean space to the manifold and then to real numbers. And so it makes sense that this goes from Euclidean space to real numbers, or some open set in Euclidean space to real numbers. And so it makes sense to talk about it being a smooth function in the sense of usual differential calculus, having infinitely many derivatives of all variables. Before we can construct any such smooth functions, one of the basic facts we need is to know the following, which I won't prove, that you can check that every compact set in any topological manifold, let's just say manifold, is closed. And that's something that you'd have to think about, and it goes back to your previous lectures in topology. So to construct lots of smooth functions, we're going to try to construct lots of little bump functions. Roughly speaking, a bump function should be something like this: dead zero, then making a little lump, maybe going flat equal to 1 for example for a while, or something like this, and then going back down again and being dead zero again. That's the sort of function we want to construct. We want to construct lots of functions like that on manifolds. So what we were going to do is we're going to take suppose we have a manifold, and MFLD or MFD or something like that means manifold, and we take a point and we take an open set, open, and suppose that the point lies in the open set. Then we want to claim there exists some function which is smooth, which f equal to 1 everywhere near this point m0, and f equal to 0 outside some compact set. Compact set contained in U. So the picture is going to be that we'll have a function, we'll have a point m0, and then we'll have on our manifold a function which is 1 near the point, and then we'll have an open set, which is some open set here, U0. So this is our open set U, and then we'll make sure that the function gets dead before we get outside of U. So you've got U as a tiny little open set, but somehow inside that tiny open set you've got to make an even tinier bump, but it's got to be equal to 1 right near there. Of course, the trick has to be that we use charts, and we identify this guy with some little open set here with using a chart with Euclidean space, and then we build our little bump in Euclidean space. So the problem is, of course, dealing with the gluing together of functions. Somehow we have to make sure when we glue we don't end up in any trouble, and we really actually do need the thing to be Hausdorff for this. The Hausdorff condition is essential here. Okay, so what we'll do is we'll just take any chart, pick any chart, let's call it W phi because we already used the letter U, around the point M0. And then we can replace W by a smaller W intersect U if we needed, so we can assume that W is contained in U. We can make it as small as we like, make a tiny little open set. Okay, so now what we'll do is we'll take in our chart, we've got, here's our point M0, and it's on the manifold M. Now we've got a chart which makes this into Euclidean space, and let's call this point, say, x0 that corresponds over here. This is our Euclidean space, our n. We have our chart, this is our phi. And what we want to do now is to pick a bump function. So we'll pick a little tiny bump function, say h of x is some bump function. And I'm assuming that you've seen enough analysis at this point that you know that there are such functions in Euclidean space, and they're supported in as small an open set as we like. So I want to make sure that my bump function is supported. The support of the bump function h is contained in a compact set K, which is contained in the open set phi of W. So now we're gonna let's see if I can draw the picture again, and I'm going to try and extend that function to be well defined globally. So what we're going to do, we've got again our point M0 inside our manifold M, and we've got a map phi of which is a chart, takes that point to some point x0. We've got a tiny little bump which is contained inside here. We've got an open set W and a larger open set U. And this guy's contained inside phi of W. Okay, and we've got our bump function, which I probably should have drawn differently, so it would be looking like it's actually equal to 1 in the middle there. And so what we do is, of course, we compose, and we're going to let f at any point of our manifold or be h of phi of m if m is in the open set W, where the chart's defined, and then 0 if m is not in W. We have to check that it's smooth. On W, f is smooth because f is identified with h by phi, and so it's fine. If we go outside W, or outside, let's say outside W bar, then f is everywhere 0, and so it's smooth because in any chart it's going to simply be 0. Now here's where we really use the compactness, because we've said that in fact so we have a point M and it's not in W, then in fact M is maybe it's on the boundary, then M is outside of this compact set K. Sorry, it's outside the image phi inverse K, because we have this compact set K, which is where K should be the support of this H. So the support of H is of course contained in phi of W, and so the support of or let's just say phi inverse K is contained in W, and this is compact. And that's an important fact. So it's a compact set, and so it's closed. Where are we? Sorry, I don't want to get off the screen there. So it's closed, and that's the crucial point. The compact sets are closed, where we're really using the Hausdorffness, and So if some point M is not in W, then M is not in the compact set K, and sorry, phi inverse K. So lies in an open set, outside of phi inverse K, where F is 0. Where F is 0. So F is smooth. Okay, and to really see that it's smooth, we've had to show that we could stay away from the problematic points where maybe there's some kind of problem on the boundary of W. Inside W we're fine, outside W bar we're fine, but right on the edge of W, maybe something goes wrong. And in a non-Hausdorff sets with smooth structure, that can happen. But in this case, it doesn't happen because we can make sure that we have compact set inside W. We have this compact set inside phi of W. Its preimage is compact inside W, and so it's closed. And therefore, its complement is open. And so if you stay away from that K, you're going to make sure that you still have H equal to 0. And so in phi inverse K, you're still going to have F equal to 0. So F is 0 on that open set, which concludes the boundary of W. So that's how the trick works. Now I want to consider some terminology that's standard in this subject. And it's unfortunate because it's quite confusing, really. Charts are a pretty simple idea. We've described them as some sort of bijections to Euclidean space, and that makes a lot of sense. But we want to think about what people call coordinates. Now, coordinates aren't that scary to you. You've already seen polar coordinates many, many times. So you know what we mean when we talk about using coordinates or working in coordinates. What we do is we start off with the xy plane, then we start talking about r's and thetas, and then we talk about functions of r and functions of theta, as if r and theta were variables rather than being functions on the plane. And that's what we're going to do here too. So if we have a chart U phi on some manifold M, then what we can do is we can think of it as associating, so as an abstract M, this is some U and it's inside some bigger M. Then what we're doing is we're taking the chart and we're mapping it into some phi of U, some open set inside Euclidean space, which I'm always drawing as somehow the plane, or it could be three-dimensional, four-dimensional, whatever. But so the point is this phi is actually somehow attaching this guy to this guy, identifying them by some bijection, right? Now that means that if we label the variables on this copy of Rn as x1 and x2 and so on, if there are more of them, then we get functions. We get just like r and theta were thought of as polar coordinates, are functions on the plane. Same way we get functions on the manifold, which are simply the numbers x1 of, well, say point M in manifold goes to x1 of M, x2 of M, the x coordinates of the point. And that's just exactly phi of M. So if you write each chart, for each chart you write out the point that corresponds. So you take a point here M, you take the corresponding point, which is phi of M under the chart, and you compute out its x coordinates, its x1 coordinates, x2 coordinates, and so on. You just write them out. So phi of M is written out as x1 of M, x2 of M, and so on. Then those are actually functions, right? So x1 is a function, which associates to M the x1 coordinate of M in the chart phi. And of course, it depends on the chart. You get different charts with different x's. So, so it's traditional to write these functions as those called the coordinate functions. So x1, x2, xn associated to some chart phi. They're called the coordinate functions. Or the coordinates. Which is perhaps more confusing to call them the coordinates of the chart. Now, mathematicians, and especially people who use mathematics, more so than people who work in mathematics, even more so, tend to just say rather than talking about a chart at all, you often don't mention charts. What if we don't mention the chart phi itself, and we just say coordinates x1 dot 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 xn. So I have these coordinates, and that's what we do when we talk about polar coordinates. We say, well, let's take the polar coordinates, r theta of the point. We think of what are its coordinates in polar coordinates. What are its coordinates in this other coordinate system? So when we change coordinates, we calculate its point's coordinates in the other coordinate system. So we think of the point as living as an abstract object in some abstract manifold, but it has different descriptions of coordinates in different coordinate systems. So rather than using the word chart, we can just use the word coordinate system or coordinates. Coordinate system, also called just coordinates. And so rather than taking a chart, we'll talk about taking coordinates, and we'll work in coordinates. It's a bit confusing, but it's actually the way in which people tend to work in differential geometry. The language of charts isn't really used as much as the language of coordinates or coordinate systems. So finally, we need to go back and figure out what did we mean by having maps of manifolds. We talked about functions on manifolds, but what's a map of manifolds? So let's think about maps. A smooth map. Let's say phi takes p to q of manifolds, so p and q are manifolds, means a map continuous in the topology so that, and when I say map from now on, they'll always be smooth maps, so that what? So that when we take charts, it looks smooth in the charts. So what I want to do is I want to say that I have some p, and I map it to some q manifold, and then what I need to do in order to make sense of this is to work with charts. So I have to have some chart that'll turn this thing, at least local little pieces of it, into pieces of Euclidean space. So little chunk of this guy becomes chunk of Euclidean space by some map, say C, and then a little chunk of this guy becomes a little chunk of Euclidean space by some map, say phi. And then I want to say that, well, then a kind of transition map-like object would be to go backwards through phi, forwards. Oh, sorry, I've called it phi, called the map phi. Let's call it capital phi. That's what I have in my notes. Capital phi. So this is capital phi here. Little phi here is one chart. Little c here is another chart. So we have a chart to flatten out p, a chart to flatten out q, and then we have a map from p to q. And what we want is this whole thing to be smooth. So that means we go backwards by phi. Little phi, then we use our map, big phi, and then we use our map, c, is smooth. And that's a map of open set in Euclidean space to open set in Euclidean space. So that's just regular calculus. When you go from this one to this one, you're actually just doing calculus. That's just calculus in ordinary variables, right? Because that lives in some plane of some variables. I don't know, x1, x2. This lives in some plane of variables, say y1, y2, something like that. And you're just doing with ordinary maps of several variable calculus. So that's what smooth maps means. That's for any charts. And of course, those charts, we have to be a bit careful where this is defined. And it might not be defined anywhere, but where it's defined, it has to be smooth. In other words, when you identify P with Euclidean space locally, identify Q with Euclidean space locally, and you check what the map does locally in those local identifications, it has to be a smooth thing. What would be an example of such a thing? Well, we could take the circle. The traditional notation for a circle is it's usually called S1 because it's a one-dimensional sphere. You should be, maybe I should say before we get into the example that it's tradition in differential geometry that sometimes, not always, but sometimes if I write x to the 3, I mean x, the three-dimensional manifold. So I don't mean 3 x's. So sometimes it's a very frustrating tradition because it doesn't mean does not mean, what does it not mean? It doesn't mean necessarily x cross x cross x, but sometimes I do mean that and sometimes I don't, and you'll have to guess when. So if I put a superscript next to a big letter, that big letter representing some manifold or some set or something like that, sometimes I mean x cross x cross x, but sometimes I don't, and I just mean x, the three-dimensional manifold. So when I write S1, you would think, S1? What do I need one copy of S? What it means is S is a one-dimensional manifold. It's a one-dimensional manifold, S. And it's traditional to write the circle as S1. And maybe just another parenthetical remark, Sn is the n-dimensional sphere. That's where the S1 comes from. The word sphere, the n-dimensional sphere in Rn plus 1, right, of the unit vectors in Rn plus 1. So that's just a traditional notation in differential geometry. And so I want to construct an example. I'm going to write this, the circle, the unit circle, and it's convenient maybe to write it in terms of, rather than real numbers, so x and y, real numbers, we can write z equals x plus iy. A complex number, it's often useful to have complex notation even if we're dealing with real quantities. And we have an obvious map from the circle to itself. Let's say phi takes circle to circle, given by phi of z is z squared. That's a nice example of it's a topologically interesting map. It takes the circle, it takes every point of the circle to a point of the circle, but it wraps around twice. When you go once around this circle, the z circle, if you let w be phi of z is z squared, it wraps twice. And you can check once we're using some charts. I don't want to do a lot of charts, but you could use trigonometry to say, well, locally at least I can represent a point of the circle by an angle. So in the notes it deals with the whole issue of trigonometry and angles and worrying about the charts. But you could say then, okay, in other words, I write my z as some e to the I theta in some polar coordinate angle theta, and then of course w would be e to the I 2 theta. When you square a complex number, you get the angle doubling. And so what we're saying is the function theta is our local chart. It's the chart, so you'd have this little phi phi is theta, is a horrible notation, but that would be a chart that locally describes where you are in the circle. You describe by the angle, and then you'd have a C map. C is is the corresponding angle of W. I don't want to give it a name since we've already got too much notation written out. But the idea would be simply that you'd check, you can do the details, to check that this map actually is smooth when you write out angles. You have to be a bit careful though. Angles aren't really globally defined, right? Because you go around and come back with a 2 pi multiple. So you have to be a bit careful. You have to do polar coordinates carefully by slicing out some angle and saying, well, I'm going to measure 0 to 2 pi or minus pi to pi, as we did before. So you can be very careful about how you measure your angles and make sure that you calculate out transition functions and so on and so forth. But you can see that this is going to be an example of a smooth map of manifolds, and not topologically an untrivial example. So let's see if we can come up with some other examples. I want to talk about the general notion of covering map, which you probably didn't come across in topology. It's discussed in some topology classes and not others. So let's look at a covering space, definition of covering space. So if we have a map phi takes P to Q, continuous map of topological spaces, then we can say it's evenly covered. Well, let's say a point Q naught and Q is evenly covered if there exists some open set with Q in the open set, Q naught in that open set. So you can take a local little picture of it. So that phi inverse of U is a disjoint union of open sets say U alpha, on each of which phi is a homeomorphism. U alpha phi takes U alpha to U. So a picture of a covering space, the standard picture is somehow we imagine that we have this is Q, some sort of large flat thing, and then we imagine that P looks something like this guy here, and then another guy maybe here, and then another guy, so on and so forth. So what we're saying is that we'd have some point Q naught, and then some little neighborhood U, and we're asking that if you go up above U and look at this is P, so it's very common in topology and differential geometry. It's very helpful to think of a map as being taking each point in space and just dropping it down. The map in this case is just simply the map that eats a point up here in P and drops it down to its shadow on this underlying plane Q. So that's a simple picture that we can have for maps, and it's a helpful picture to think about maps as being some kind of shadow picture. So we have all these layers of P, and they map down to Q. This set U here then has some preimage up in P, which is something like this, and it's copies. There's some sort of U alpha 1 and there's some sort of U alpha 2, and each of the U alphas is mapped perfectly by homeomorphism. So if you're inside this this U alpha 1, you look down at U and you see there's a perfect matching up. Capital Phi is exactly matching up those open sets, and the same from inside U alpha 2 and so on. These are called sheets. These are called sheets. Have I gone off the edge? Okay, sheets. So the main thing to keep in mind is this sort of picture that near the points of Q, you can make little open sets, and so that the map actually just looks like a projection of all those different homeomorphic open sets. They're all homeomorphic to that U downstairs. They're evenly covered, and a covering map. Is a map so that every point Q naught in Q is evenly covered. Okay, and then there's a trivial observation that if you have this sort of covering, so a covering space, the definition of a covering space is some P, so that we are given some kind of covering map. Okay, so a covering map is a map so that every point's evenly covered. They all have these things look sort of the same. They all have this kind of picture, and then a covering space is a space so that we have a covering everywhere. So that they have this covering map property. So when I say something is a covering space, what I mean is that I really have a particular map in mind, phi, that does the covering. So when we talk about it being a covering space, that's a bit sneaky. We really mean actually this map, and I have to know what the map is to say that P is a covering space of Q. I really mean P is a covering space of Q with respect to a given actual map. The map really has to be part of the data of the P, but if we like to talk about P as a covering space of Q, it's a more natural terminology. So then if there are countably many sheets, and let's say Q is a manifold, clearly then P is also a manifold. Why? Because take a chart on, a little tiny chart. If you take a chart with a domain that's small enough that it lives inside this U, then you can compose it with these homeomorphisms, and you get it exactly matching up with these sets up in P. They're all homeomorphically identified with that same set in Q, and then if you change chart, well, you change chart in Q, and then you pull back the charts, you compose the charts with this capital Phi, and so they match up. They are exactly identified with the transition maps are identified with the transition maps down in Q. So it's clear that's a construction of new manifolds from old, these covering spaces. Moreover, the covering map is also a local diffeomorphism. It's not a global diffeomorphism maybe, but it's a local diffeomorphism. So that gives us very important examples. Let's see what some of those examples are. And the simplest case we can come up with is the theory of orientation of manifolds. It's a very basic and fundamental idea because we often have to orient manifolds in order to carry out integrals over them. Let's think about how we orient things. So if we had a curve in the plane, well, maybe I shouldn't draw endpoints for it, but anyway, we have a curve in the plane, you could go that way along it, but you could also go along it the other way. And you could think of those as two different ways of dealing with that curve, almost as if they're two different curves. So an orientation of a curve should be a choice of which direction to go along it. What's an orientation of a surface, though? You can't have a direction you go along a surface. But if you were a chick, you might live inside an egg. And if you were a chicken, you'd only live outside an egg. So it has an inside and an outside. So for a surface in three-dimensional space, we want to say the choice of an inside and an outside is something like an orientation. It picks out which is the inside of the surface and which is the outside. We're familiar with this from working with Stokes' theorem with integrals. So you have to do your integrals sometimes with careful orientation, and you have to make sure you know which side is which of a surface. This works well for surfaces in three-dimensional space, but for a surface in higher dimensions, it doesn't actually have an inside and an outside. So we have to have a somewhat more subtle definition. And it also doesn't work even for surfaces that are in Euclidean space. There could be a problem. The classic example is something like, if I could draw it, something like this. If we make a little hexagon and smooth out the sides a bit, then we should be able to make a drawing that goes something like this. This side goes over here, I think, and then this side wants to go over, what do I do? This side goes over here, and then I hope I've got it right. Something like that. And if I were to smooth it all out, you could see that, if I drew it really nicely, that sort of piece of paper, it's a strip of paper. What we've done is just to take a strip of paper, or you could do it with a belt. It's very easy to do it with your belt. You twist it. So we twist it so that this side going this way is glued to the opposite side, but going the opposite way. And you get this kind of object, maybe a strip. And you can see that it doesn't have two different sides. It doesn't have an inside and an outside. So that's important. It's not possible to pick an orientation on it. Okay, so how do we pick an orientation on a general manifold? We seem to have two very different notions because one of them is direction along a curve and the other one is sort of an inside or outside. But that, as I said, only works for 3 dimensions, for surfaces in 3 dimensions. So we need a better definition. We can say that an orientation comes about by picking orientation preserving charts. But what are those? So a diffeomorphism. So taking, let's say, some open subset of Rn to some other open subset of Rn. So diffeomorphism between open sets in Euclidean space is said to be orientation. Let's call it, again, I don't know, I need a name. Let's call it phi. Orientation preserving. Said to be orientation preserving if the determinant of the derivative is positive. What's a derivative? If I have y equals phi of x, then I can write that as y1 of x dot 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 yn of x, or whatever, however many there are. And then you're familiar with the notion of the matrix of derivatives. Phi prime, for me, is the notation that I prefer to use for the matrix of partial derivatives of dyi dxj over all the i's and j's. In other words, it's the matrix which has these sort of entries. Okay, so that's a convenient notation because it really fits in well with one variable calculus notation. But if you use a different notation, some people prefer d phi, or some people just prefer to call it dy dx, or whatever you want to call it. That's fine. So this the notations quite frequently change among people who work in differential geometry. Different people like different notation. So so that's how we can talk about orientation preserving if we're dealing with just open sets in Euclidean space. But then there's an obvious definition for a manifold. We can say two charts. On a manifold, two charts U phi and VC are compatibly oriented. If the transition map is orientation preserving. So they agree on what orientation they give because when you use one to orient and use the other to orient, they have a transition map that tells you how to go from one to the other, and it's orientation preserving. So that's what we'll mean by it. So an orientation is going to be a maximal atlas. Again, we like maximal because we want to use like a smooth structure. We want to use allow all the charts we can. We don't want to restrict which choice of charts we use. We have a maximal atlas subject to. So it has to be an atlas. It has to be maximal. Must be subject to compatible orientation. So they have to be all orientation compatible. Orientation. Sorry, I'm getting a bit squished in there. So that's the idea, that you'd want to make sure that they all agree about how to orient the thing. And that'll give you a notion of orientation of a manifold, right? An orientation of manifolds, a maximal atlas, subject to the requirement that any two of the charts have to be compatibly oriented. This gives rise to a very nice example of a covering space. And I won't go into detail proving that it's a covering space, but it's a nice example of the use of all this theory to construct new manifolds out of old. And it really uses the fact that we're dealing with abstract manifolds, not given concretely as surfaces inside three-dimensional space, but as abstract geometric objects. All right, so M is a manifold. And then let's let, let's call it, say, M hat be the set of choices of points M and little o, such that M is in M and O is a local, I'll say what this means in a second, local orientation for M near little m. So all the choices of local orientations. What's a local orientation? A local orientation of M near a point M, let's say M naught in M, it's a choice of chart, say U phi, but up to equivalence. WC is equivalent if phi and C are compatibly oriented near, not everywhere, but just near that point. So we don't have to have them globally compatibly oriented. So that gives us an idea that we locally orient. So the picture, you sort of somehow have a chart defined for this guy. You somehow chart it with something. But you get to change the chart. It doesn't matter if you use a different chart from me, it's fine. They're equivalent as long as they agree about the orientation near the point. And that's how we can define orientation near a point. And if we define M hat to be the set of choices of point and nearby orientation, so for each point it picks out an orientation nearby. And then there's only two possibilities, though, because up to this our equivalence, the chart is either going to be compatibly oriented or incompatibly oriented near that point. They're either going to give the same or the opposite orientation near that point. And so the transition map either is positive determinant or negative determinant. And so there's only two possibilities. And so in fact we have the map. Let's call it pi takes M hat to M, given by pi of point and local orientation is just point, and that's 2 to 1. And in fact, it's a covering map, which is again something you can check. It's a nice example. And so that means that in fact for any manifold M we have an abstract, it's 2 to 1 because there's two possible orientations. And we have an abstract example of a construction of a new manifold from an old one. We started with any M, we construct an M hat. It's always a 2 to 1 covering because it chooses one of the two possible orientations near each point. And I'll let you check all the details. And then if M is like the Möbius strip, is not orientable, it doesn't have an orientation, it has no orientation, there's no choice we can make of charts that are oriented, then M hat is always orientable. Well, I should say whether M hat is orientable or not. M hat is always orientable, which is something that you can prove as an exercise. So that's quite impressive. We've constructed an oriented covering. We started with a manifold which may or may not be oriented. We constructed this covering, and in fact we can say M is not orientable. It's another exercise if and only if. Well, let's say I should say suppose that M is connected. Suppose M is connected. It's one piece, one topological piece. Then M hat. Let's see what I want to say. M is not orientable. M is not orientable if and only if M hat is connected. Okay, so it means that we get a nice picture of how to orient a manifold. It's an unorientable manifold like the Möbius strip. Well, there's two possible orientations. Let's pick both of them and make a new space, which is just something like a choice of which side to be on in the Möbius strip. What it does, it constructs something like the Möbius strip, but that's twice as long as the previous Möbius strip. In a picture, if you thought about the Möbius strip, which I don't really want to do because it's hard to draw, I didn't do it very well, but if we drew it like this, as a picture like this, where we think of that thing as being identified in the opposite ends, what you could do to construct a 2-to-1 cover of it is to take two copies, like this, and then do it again, like this. And then, of course, if you glue them, you glue that end to that end to make, you glue that end to that end to make the Möbius strip. But if you glue that end to that end to make a 2-to-1 copy of the Möbius strip, and that'll be the M hat. And that's the M. There's the Möbius strip, and there's its 2-to-1 covering. And that is orientable. Why is it orientable? Because if you glue that strip to that strip, you just get a usual cylinder. You get a standard cylinder. So you can see that this is the Möbius strip, and this is its 2-to-1 cover, which is a cylinder. So it gives a nice example of manifolds on maps between them. I mentioned before that another important class of manifolds and maps that we can come up with is we take a given manifold and we try and quotient it by group action, and sometimes the quotient will actually be a nice manifold. There's a lot of technical detail here to make sure that it works, because sometimes it works and sometimes it doesn't work. It's a bit subtle. So we want to think about quotients. When are they manifolds? So we want to think about actions. What's an action? It means we have a group acting on a manifold, and usual sense of a group action. But for us, we're not going to just want it to be that on a manifold M. So for each element of the group, we have a smooth map, which associates to each point of the manifold and GM in the manifold. Okay, so it's going to take an element of the group. Each element of the group G is going to act by a smooth map of the manifold. It's going to smoothly map on the manifold, and so that, of course, it has to be a group action, so it has to satisfy the usual properties of a group action. These guys, 1 M is M. Okay, so the usual property, this is for G, H, and gamma, that when you compose the maps, you get the group product operation, and that the identity element acts trivially. And we say that it's free. These are all standard for any kind of group theory, but we're requiring our maps be smooth, right? That's the only difference so far from usual group theory, that our actions have to be smooth maps, and it's free if for any x in M, gx equals x if and only if G is the identity element of the group. I'll write my identity elements as 1 in the group. And well, let's say for all G and G. So only the identity element fixes a point. Then the orbit. The orbits are, we write gamma M for the set of all GM such that G is in gamma. Okay, so that's the orbit of the group, the usual definition of orbit. And the quotient space is just usually either written as gamma mod M or M mod gamma P. Most people like the second one, but there actually are reasons to have them both around. It's the set of orbits, the set of all orbits. Okay, and with the quotient map, which I'll usually write something like pi. takes M to M mod gamma, given by each point goes to the orbit of that point. Each point goes to the orbit of that point. Okay, so that's the definition of the quotient space and the quotient map, and you give the quotient space the quotient topology with the quotient map. So everybody's happy as far as topology is concerned. Topologists don't mind. To them, this is perfect. There's no problem. But for us, it's a very difficult issue. When is it actually a manifold? Is it a manifold? Is it not a manifold? And another definition we did is that a group action is said to be proper. The action is proper if any two points of M from, and this is a special condition proper. Most of these actions, many actions are not proper. Some actions are, some actions aren't proper. An action is said to be proper if any 2 points of M from different orbits lie in disjoint gamma invariant open sets, not just any open sets, because when we're starting to work with group actions, we have to think about invariance. So they have to line gamma invariant open sets. Okay, so those are all the definitions we need about group actions. Let's go back over them. So a group action is going to be some group acting on a manifold, but it acts by smooth maps. So each element of the group transforms the manifold from each point M going to GM according to some smooth map. And when you compose the maps, you multiply in the group, and the identity element extrivially fixes every point. The maps, I've changed my notation somehow from little m's to little x's, but whatever. So the action is said to be free if the only element of the group that fixes any point at all is the identity element of the group. And the orbit is the obvious thing. The places where the group takes a particular element, M, a particular point. Where does it go to under the group action? And the quotient space is the collection of all orbits. We treat each orbit in the manifold as a point of the quotient space, and it has a quotient map and a quotient topology. I didn't write that down, but also has obviously a quotient topology. Every quotient has a quotient topology. So, we now have this notion of proper. A group action is said to be proper if any 2 points from different orbits lie in disjoint invariant open sets. Okay, so that's the collection of all the definitions we need to be able to get started on writing down some kind of statement about quotients when the quotient is a manifold. So here's the result, which I'll only outline how to prove. If a group acts freely and properly on a manifold, and of course smoothly, it's a smooth action, that's understood, then M bar is sometimes right for the quotient. Okay, quotient gamma mod M has a unique manifold smooth structure. So it's a smooth structure and makes it into a manifold, so that the quotient map is local diffeomorphism and a covering map. So diffeo for diffeomorphism and a covering map. So that's what you need. You need free and proper. It's not the only case under which this would happen. There are other group actions where it might still happen, but it's good enough for us for lots of examples. So we'll want to be working with simple, very, very simple group actions. Free and proper actions are very, very simple ones. And we'll see if we can construct some examples. So some outline of the proof before we go on to do examples. Let's think a little bit about the proof. I don't want to do very much of it. The Hausdorff property is essentially trivial. That we can check because the properness of the action is exactly that there are these invariant open sets upstairs in M, but they correspond exactly to open sets down in M bar, in the quotient space M bar or gamma mod M, whichever how we want to describe it. So Hausdorffness is really just exactly the proper condition. the basis of countable basis of open sets of M then descends to produce open sets down in M bar, so that always has a countable basis too. So that's never a problem. It's not hard to prove using general topological arguments, which I won't give, and they're given in various in my topology notes for the topology class, for example, that that the action is actually a covering action. So it's actually a covering map. So it's sort of there's insert some topology here, maybe from my lecture notes or somewhere else, that gives you as a covering map, that the pi is a covering map. So I won't deal with that in any detail. But then, just as we had the general construction of a covering, saying that if you had a covering space, you could use charts downstairs on the downstairs manifold to pull them back and to compose them with the quotient map to make charts upstairs. The same thing works the other way. Given charts up on M, you'll take some chart here, and then you'll compose it with the inverse of the covering map. Because this pi is a covering map, you can make the inverse go the other way, and you can use that. You can go up here and then use your chart and call that a chart down on the quotient, and that'll actually produce charts. And you can check the details are given in the lecture notes that actually works and gives you a manifold structure. So let's just treat that as more or less understood, hopefully, and we'll be able to now use it in some examples. So one nice example is the Klein Bottle. These examples are a bit hard to draw, but let's try to draw the Klein Bottle. Klein Bottle, rather famously, is supposed to look something like a bottle, but it's supposed to have a kind of neck that goes out and comes back into it. Something like this. And then once the neck goes in, it's supposed to spread out and become the base of the thing. So it's possible to make it look something like that. That's about the best I can do to draw it. Let's see if we can get a picture of one. It's not a very good angle. Let me see if I can get the camera a bit better. There we go. There's a Klein Bottle. So you can get a sense of what it looks like. Okay, so let's get back to thinking about it though as a quotient. Manifold, how do we actually produce it as a quotient of something by some group action? So we want to think about taking a little box in the plane and drawing a quotient by saying that we're going to make this side and this side be matched up. But we're going to make this side and this side be matched the opposite direction. And that'll produce a Klein Bottle. How will it produce a Klein Bottle? Putting these two together will produce a cylinder. Right, just the top and bottom glued together, and they produce this cylinder. Now this end is supposed to be going now this way, and this other end should be going the opposite way, right? So it would go like this, maybe. It's not a great picture of it. And then you're going to glue those together, but to glue them together, you can't make just a torus. You don't make a usual torus because this is going the wrong way for a torus. So what you do is you make this end go. Can I draw it? Let's make this one quite a bit bigger, and then we'll make it go narrow down toward the other end. Just continuously deform it, and then this end we're going to bend around. So now let's see. Now this goes like this, and then hopefully this one also goes that way too, if I've got it right. Yeah, I think that's right. So that if it was, yeah, that looks right. So then what you're going to do is you're going to take that guy and you're going to allow it to go back in inside itself. So it goes something like this, and then once it's inside, it's got a little hole in it like that, which hopefully goes like this, and then this goes like this. And now you can see that you can actually glue the two together. It's not a very good picture, but you can glue these together. This guy's going to end up glued onto that like that, giving you the Klein Bottle. Okay, and that means that from that point of view, this guy is in fact given by taking the quotient by, well, what are we doing? We're going to move this guy up by 1 unit and glue it together. So we're going to make a group action that it involves certainly this group element. It's going to take the xy plane, it's going to take this unit square, and it's going to move to x, y plus 1, and that will glue the bottom to the top of the square. Now we're also going to take the other problem is to glue the other sides, but the opposite way. So we're going to glue this one onto x plus 1, moving us 1 unit over, but then minus y. Okay, so that operation will slide us 1 over and flip the thing upside down, so that this side gets moved over to that side, flipped upside down, and that'll glue it together. So we get a group gamma, which is generated by those two transformations. And they act on R2, the plane. They act on the whole plane, but that's okay because they'll move every 1 by 1 square to every other 1 by 1 square eventually if you carry them out enough times. And they'll move this side of this 1 by 1 to that side with the opposite orientation, and this top to the bottom, and glue them together. And so that'll give us a quotient. And you can check that this is actually a free and proper action, which I won't do in detail. So that gives you that the Klein bottle is actually a surface. Okay, so that's a nice example. The Klein bottle is really a surface. A more elementary example is that the torus is a manifold, usually written as something like Tn, the torus, and it's simply Rn mod Zn. The action is this guy, so this is the group gamma. It's just the integer elements of the vector space, the integer vectors with integer coordinates acting on the manifold M, which is just Rn Euclidean space. So you get non-trivial examples, and both of those, the Klein bottle and the torus, are both examples. I should write this as an example. They're both examples where the original space is Euclidean space. So already starting with boring manifolds like Euclidean space, we're beginning to construct serious examples of manifolds, which are much more interesting topologically. Already there are serious examples that are very simple quotients of the much more elementary examples. Another example that is almost the same sort of story is the real projective space, RPN, which is, of course, the projectivization of the vector space Rn plus 1. It goes down in dimension when you projectivize. You modulo out by rescaling. And so it's an n-dimensional manifold. And what is it? Well, it's really just given by taking the unit sphere Sn contained in Rn plus 1. That's going to be our manifold. And then what we'll do is we'll simply quotient by gamma is the group of numbers plus and minus 1. And we'll get gamma to act on the sphere by saying each element of gamma in gamma is a plus or minus 1, and each element in the manifold is some vector, some unit length vector, because it's the sphere of unit vectors in n plus 1 dimensions. And then we just get it to act by the usual gx is the usual multiplying by plus or minus 1. And so the quotient is m mod gamma is, of course, the sphere modulo plus or minus 1. So it consists of all the unit vectors, except the vector's not really well defined. It's only defined up to sign, up to a plus and minus sign. And that, I'll leave you to think about, is exactly the real projective space, the projectivization of a vector space. It's exactly, it's the set of lines to the origin in a vector space, because each line passes through a unit vector. Each line through the origin has a unit vector in it, but the unit vector isn't uniquely defined. It's defined only up to plus and minus 1. So we get a serious example, and again, that's a free and proper action, as you can easily check. So we've now started to develop some techniques that are making it possible to construct serious examples using maps. And in particular, the maps in this case aren't just a single map, but maybe a whole group acting by a whole group of maps. And we can take some kind of quotient of this group action, for instance, giving us serious examples. But there are going to be other examples that come from other sorts of maps. For example, embedded submanifolds arise in some sense as maps. So we can see that we're giving rise to lots of interesting new manifolds by simple techniques. Once we have a notion of function, we get a notion of smooth map. Once we have that, we get a notion of how to do various things like quotienting, and so we are able to construct new manifolds out of old. As I said before, we end up finally at some point where we have such a large collection of manifolds to work with that we almost never write down charts and write down transition maps. We just use the ones we already know from the existing stable of manifolds we've already worked with and try to construct new manifolds out of old much more than actually constructing any sort of real new manifold directly from charts. Now, differential geometry is supposed to be about taking derivatives. It's supposed to be about differentiating. We haven't differentiated anything yet. So next time we have to figure out how to differentiate maps. And then we'll use derivatives and we'll use calculus to try to go from local to global constructions so that we can be able to use calculus and check conditions locally by differentiating things in charts, and actually see that we can get global results about construction of new manifolds from old. So this will really be a way to begin to start putting calculus into the picture, so that we can use calculus constructions to do differential geometry.